Um, I'd like to thank Source for. I'd like to start by saying thank you to Source for inviting me out here to the East Coast and for giving me a venue to offer this presentation. My name is Bill. I'm from below Gotham, and today I'm here to talk about rootkit technology and where I think things are going to be headed, maybe over the long run. I'm going to start with a story. There was a story that popped up in the media a couple of years ago. I think it was 2008. There's a story about a Japanese bachelor who lived alone in a western city in Japan. And over this series of several months, he noticed that food had gone missing from his kitchen. And he's like, what's going on? Maybe is someone coming to my house and stealing my food? So he put up a security camera and had it stream photos to his mobile phone. And one day he gets a picture. There's someone in his house walking around, and he's like, "Oh my God!" He calls the cops, and they rush over thinking we can catch this burglar, and catch him in the act. So the cops rush in, sirens blaring and everything, and they notice that the doors are locked, the windows are all closed. They're like, what the heck? So they search around the house and they open a closet, and they find this woman curled up in a little ball at the bottom of the closet, and they question her. And so, according to the woman, she's been living there for a little over a year, and she's homeless, didn't have a place to live. And the guy left his door unlocked one day, and she found her way in. And the police spokesman, who the press people talked to, said that she was notably neat and clean. She took showers, she did all sorts of stuff, and she moved a mattress in under the bottom of the closet, and he just never knew she was there. And in a sense, that's what a rootkit is. It's an intruder that's notably neat and clean, and maybe even difficult to get rid of. In terms of implementing a rootkit, one way to stay neat and clean is to stay memory resident. That way, if the investigator powers down the machine and does a post-mortem analysis, they won't find anything, anything outside of the paging file. If they're lucky, they'll find something in the paging file. They might not know what it is. And so, anyways. But even if you decide to stay memory resident, there's two challenges that you're going to face. And these kind of define our design requirements. I mean, if you were going to build a rootkit, and want to make it memory resident, there are two issues. The first one is avoiding someone doing memory analysis at runtime. Some investigator doing an incident response a live incident response is going to maybe do a perfunctory analysis of memory. That doesn't happen a lot. Even the people who sell the software that does forensic analysis will admit that it's still kind of an emerging area that people are working on. And you also have to worry about surviving reboot, obviously. If you're memory resident, the machine goes off, you're toast. So we can recast these two items as requirements, as design goals for a rootkit that's memory resident. And so let's look at the first one, avoiding memory analysis or concealment, basically. The old school approach is to hide in a crowd. So you either you create a new process and you rename it so that it looks inconspicuous and camouflages in with existing processes. There's a whole bunch. And if you're a harried system administrator, you don't have a lot of time. Sometimes it's very easy to look over the task list and just skip something entirely. Or you can maybe inject a DLL or a thread into an existing process. That's another way to kind of hide in a crowd. Now, the catch is that this approach, it's kind of an age-old approach. It works maybe in the short term, but it won't survive the standard forensic incident response process. In fact, if you read books like Harlan Carvey's or Richard Balick's, this methodology that exists today is meant to capture stuff like this, and it will. If you do a rigorous process, you'll find it eventually. When I started at San Francisco State University as an IT guy, I walked into this college and it was a war zone. There wasn't even a firewall around anything. We had all of our faculty, staff, machines. internet addressable IP addresses. Some of them not even had didn't even have like the Windows firewall activated, and it was just like, you know, there were bullets flying everywhere, you know. They got all of our servers. They compromised our domain controllers. And one thing they did, which, you know, looking after the fact is kind of interesting, they took our web server and they activated the Windows Update services, the SUS servers, right? They set it up so that it started. They changed the group policy for the domains so that all of our client machines pointed to this SUS server for its updates, for their updates, and it streamed out this package, this MSI package. It was a cracked version of Dameware, and so which is basically a remote desktop, you know, application, which has legitimate purposes. In this case, it wasn't legitimate. So all of our machines had Dameware on it, and so you look through the process. First thing I usually do is look through the process. You know, if you looked through originally, there was this process in the task list called rpcnet.exe, and you might skip it initially, thinking, okay, it's an RPC service or something like that, but it wasn't. It ended up being something else. And so just, you know, if you do the standard response, the standard live response, you'll catch this stuff. So they responded, you know, the hackers responded and saying, okay, well, what we'll do is we'll rely on system modification to hide stuff after the fact. We'll install stuff, and then we'll modify the underlying operating system so that it hides what we install. And there's a bunch of ways to do that. You know, there's hooking, detour patching, and other stuff. You want to manipulate dynamic stuff, decom, and callback tables that you can kind of subvert. And so the problem with this approach is you're hiding stuff after you have actually launched the module. So there's a certain degree of bookkeeping data structures that are updated in the operating system. So you've launched this module, and then you've altered the system to hide stuff. But you can only hide so much before it's not executed anymore. If you want the code to execute, it still has to be registered to some extent with the operating system. And this is kind of what a lot of security software relies on. It's like, okay, we'll do a cross-view detection where we'll look at the system from a high point, you know, at the API level, and then maybe we'll parse data structures directly and do a low-level analysis and then compare the two. And sure enough, if a lot of these tools will catch stuff because you can only hide so much before the kernel's not scheduling your code to execute anymore. Some of the vendors who sell security software have actually wised up to the fact that APIs and stuff and libraries can be subverted at runtime by a rootkit. So they said, okay, we're gonna sidestep the APIs altogether. What we're gonna do is we're gonna parse stuff in memory directly. We're gonna start off, and then we're just gonna, you know, manually go through everything without relying on the API to do it for us. And that's not a bad approach. What that resulted in was, okay, the Black Hat said, okay, we're going to take this one step further. We're going to move to a mode of execution where we're outside what would normally be considered the operating system proper, and we're going to jump into these kind of out-of-bounds regions and rely on those. You know, the typical, you know, what I have here is like the rogue hypervisor, the SMM mode rootkit, and the AMT environment, which are basically what you would consider ring -1, ring -2, and ring -3 rootkits. The Intel processor supports 4 rings of execution of protective, you know, privilege levels in the processor. Windows only uses 2 of those. Primarily, it has to do with historical kind of portability reasons. When NT first came out, they wanted it to run on MIPS. They wanted to run on DEC Alpha. They wanted to run a whole bunch of stuff. And Intel was just another chipset. So they didn't want to, you know, anchor themselves to the foibles of one processor. So they didn't use all 4 rings that the Intel processor offers. And so there's only, for historical reasons, you really have a 2-ring model. You have the user mode and the kernel mode. And with these extra features that get added on, you have actually rings within that. You know, the ring 0, which is kernel mode, and then the ring -1, which is what hypervisors will execute in, and SMM mode